Welcome to Groups. Homomorphisms, this is proposition 19. A finite cyclic group of order n is isomorphic to Zn plus. So what are the members of Zn? Those are the modulo classes n, 0 bar, 1 bar, 2 bar, dot, 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 n minus 1 bar. And what this proposition means is that any finite cyclic group of order n is the same as Zn. And in a sense, we might as well just study Zn instead of different types of finite cyclic groups, right? So let's look at the proof. Now, since G is a finite cyclic group, it has a generator. Suppose the generator is A, then A square, A to the n, for some natural number n will be equal to E. Since it's finite, it can be generated by one of its elements, say A, then the group consists of A square, A cubed, dot, dot, dot. There will be some natural number n such that A to the n equals E, the identity. So we'll define a homomorphism F from Zn to G in this manner. Every element x bar in Zn can be mapped to A to the x, where 0 less than or equal to x less than or equal to n minus 1. We will first prove that F is a homomorphism. Then we will prove that it is one-to-one and onto. Onto is always fairly straightforward, and that will establish that F is an isomorphism. So what do we need to show that F is a homomorphism? We have to start with f of x bar plus y bar and end up with f of x star f of y, whatever the operation of G is, right? G has some operation, G star. So f of x plus y is equal to ax plus y. That's the homomorphism. That's how it's defined, which is of ax, ay, and that is just f of x, f of y. So that establishes that f is a homomorphism. Next, let us establish that f is one-to-one. In order to establish that a function is one-to-one, we'll start out with f of x equals f of y bar and end up with x equals y, right? Okay. So f of x equals y bar implies a of x equals a of y, and that implies a of x over a of y equals 1. And that means a of x minus y equals a of 0. That's what 1 is, a to the 0th power. And in this language, and that is x minus y equals 0, so x equals y. And lastly, we will show that it is onto. Onto is usually very straightforward. It just follows from the definition. Usually, not always. It certainly is straightforward here. For every element a to the x in G, there will be an x bar in Zn such that f of x bar equals a to the x, right? 0 less than or equal to x less than or equal to n minus 1. Thus, we have f is a homomorphism, f is one-to-one, f is onto, and we may conclude f is an isomorphism. And that means Zn is isomorphic to G. That's the end of the proof. I'll see you in the next segment.